We present a high-quality and high frame rate 3D depth capture technology that is capable of 210 frames per second capture of arbitrary scenes. We show how this is immensely useful to a variety of computer vision applications where the pose of an object or person must be tracked from one frame to the next. The value can be seen here, where we are running a non-rigid reconstruction pipeline. As shown on the left, traditional frame rates can quickly cause tracking errors, rapidly leading to catastrophic failure in the reconstruction. Although there have been many different active depth estimation technologies proposed over the years, most of them are low frame rate or suffer from motion artifacts. It is true that ultra-fast stereo depth algorithms have recently been proposed. However, they've only ever been coupled with low SNR active illuminators, requiring exposure times inconsistent with actually running at high frame rates in practical settings. Our system compares favorably to traditional 30 frames per second systems, such as the Structure I/O or Connect V1. These can be seen to suffer more from depth quantization, edge fattening, and motion artifacts. Time-of-flight cameras, such as the Connect V2, can suffer from distorted geometry due to multipath and other motion artifacts. Here we take a closer look at our depth technology, which is running at 210 frames per second. Notice how the quality is not degraded despite running at these high frame rates. Notice how we can slow down the sequence and show that frame-to-frame motions are extremely small. It is also extremely low latency because we process each frame so quickly to achieve these frame rates. Notice how the system does not suffer from motion artifacts, given the low exposure time of the camera. Our reference hardware is based on commodity components. In combination with a VCSEL-based illuminator, we use high frame rate infrared cameras which are based on equivalent RGB mobile phone sensors used for slow-mo video. Next we show results of using our high frame rate sensor for rigid scene reconstruction. Here we see that at 30 frames per second, the accumulation of drift is far more evident. In the end, this leads to gross tracking failures. Instead, at higher speeds, our system reduces per frame errors and leads to more convincing reconstructions. In another compelling example, we show how our high frame rate system aids the tracking of the articulations of the human hand. At 30 frames per second, we see much frame-to-frame error, jitter, and latency. In contrast, at 210 frames per second, we see a massively improved tracking pipeline. Next, we show tracking results of a template model of a human body. Notice the tracking failures at 30 frames per second that are rarely seen at 100 frames per second. We also demonstrate full-body reconstruction using a multi-view system built with our sensors. Note that our sensors do not interfere with each other. Here there is very complex motions and poses being taken by the user and faithfully reconstructed. We show the motion field representing the robust tracking of the user over time. We also apply our system to face tracking. Most face tracking systems need to rely heavily on RGB key point localization. We find, however, that we are fairly robust using largely geometric cues based on the depth image, due to the high frame rate and the low interframe motion it yields. We can also use our sensor to bring mixed reality experiences to virtual reality. Here a single sensor is mounted on a Vive VR headset. We then reproject the captured depth and color data into a point cloud that is viewed by the user. The overall latency is sub 20 milliseconds, allowing for complex human-to-human motion and interaction in the scene, without the user feeling discomfort or nausea. For example, a user will struggle to catch a ball due to the latency typical 30 frames per second systems would induce. In contrast, with the lower latency afforded by a higher frame rate, the user is able to easily catch the ball.